who is a postdoc with Susan Murphy at Harvard. He completed his PhD at University of Michigan, and he's been focusing on things around reinforcement learning for mobile health settings. So I'm very excited to hear his talk. Thanks for joining us.
Thanks. Thanks for the introduction. It's my great pleasure to be part of this very exciting workshop. I benefit so much from attending the talks over the past few days. So the topic I'm going to present today is the batch policy learning in average reward Markov decision process. This is a joint work with Zhengling Qi at George Washington University and my advisor, Susan Murphy. I apologize if you can hear the noise in my background. There is some repairing work that is happening right up above my head. So let's get started. So this work is motivated by the mobile health applications. The technological advancements in mobile sensing allows us to not only collect data in real time, but also to deliver the interventions anytime and anywhere. Ideally, we want to use these real-time collected informations to deliver what we call the just-in-time adaptive interventions. That is to deliver the right interventions to help the users to achieve their health goals and maintain the healthy behavior over a longer period of time. For example, to help the users to increase their physical activity or to reduce the stress or even to help them to quit smoking. Many mobile health interventions are designed for long-term use. On the other hand, most of the currently deployed interventions use expert-derived policies with little data evidence. In this talk, I'll be focusing on the batch setting. I will present an approach for using the pre-collected data to learn the treatment policies that can optimize the long-term performance when used in the future. So let's talk about the problem setup in more detail. So on each individual, we collect data over capital T time points. We use the standard notations in reinforcement learning. S represents the states, A is the action, or sometimes I call it treatment in the context of the mobile health, and R is the reward. In the mobile health, the reward is typically the health outcome measuring the near-term effectiveness of the interventions. And we are in the batch setting, so we cannot control how the actions are selected. So the actions are selected by the behavioral policies. In this work, we do not require to have access to the behavioral policies. Also, the behavioral policies is allowed to depends on the entire past history arbitrarily, not only the current state. So we'll be focusing on the settings where the training data consists of an RID copies of the trajectory of length T. So we use the Markov decision process framework. So we assume the Markov property for the evolution of the states, and we assume the state dynamic is stationary. So for a given policy pi, we define the long-term average reward, or the average reward for short. In general, the average reward is a function of the states. But when the induced Markov chain is irreducible, the average reward becomes a constant and equal to the expected immediate reward under the stationary distribution. And the existence of the stationary distribution is guaranteed by the irreducibility. These are the standard results in the average reward MDP. So why we are interested in using the long-term average reward to evaluate treatment policies? Remember, the goal here is to optimize the long-term performance of the mobile health policies. So the average reward provides a high-quality proxy for the expected average reward over a long period of time. The reason why this is we think this is a high-quality proxy is because the error decrease in the order of 1 over T star, as opposed to the usual 1 over square root T. Of course, here the leading constants will depends on the mixing time of the induced policies, and we use the average reward to serve as a proxy for the long-term average reward for a long period of time. That's the motivation for using the average reward, and we consider a pre-specified parametric policy class instead of directly estimating the unrestricted optimal policies. We use the policy class. This allows us to kind of borrow the domain knowledge to construct a policy class. For example, to choose which variable is important for decision making, and so that we can put that in the policy. And also this can ensure the interpretability of the learned policies. The goal here is to efficiently learn the optimal in-class policies using the pre-collected data of NIID trajectories. The efficiency here is a big consideration for this work because the amount of the data in health application is often quite limited and could be expensive to collect. To efficiently learn the policy, we propose to first construct the efficient estimator for the average reward of a given policy, and then we perform the policy search by maximizing the estimated average reward. So that's the setup. So we will use the semi-parametric theory to kind of inform the efficiency estimator, where we treat the average reward as the parameter of interest. So here's just a quick one slide review of the semi-parametric statistics. We have this notion of the semi-parametric efficiency bound. This is essentially the asymptotic lower bounds on the variance of the estimator for the parameters, and the efficiency influence function is the influence function of a regular estimator that achieves the semi-parametric efficiency bound. Roughly speaking, an estimator is called regular if we can have this linear representation. Here, the phi is called the influence function, kind of capturing how the error, how each data influence the error of the estimator. It's a standard procedure in statistics that we use the efficiency influence function to construct the efficiency estimator, and this is the approach we're gonna take here. So just introduce a few notations. We use the qpi to denote the relative value function, the state action value function, and we use dpi to denote the stationary distribution of the state action pair for the policy pi, and we use the d of to denote the average distribution of the state action pair, averaging over t decision times in the data set. We remember the data set is collected under the behavioral policies. So each of these little t, the dd is the marginal density for the state action pair at that specific time point, and we take the average. Under some regularity conditions, we can derive the efficiency influence function for the average reward given the data set of NIID trajectories. This involves the ratio of the two density and also the relative value functions. Yeah, the term in the parentheses is the TD arrow. So the efficiency influence function is essentially like the average of the weighted TD arrow at the true value. Right. So for simplicity, I will use the upi to denote this difference of the value of the relative value function at two different states, and we use the omega to denote the density ratio. With these two notations, the efficiency influence function can be written as this simplified form. Suppose we are given some estimator for these two nuisance functions, u pi and omega pi. We can then estimate the average reward by solving the plug-in estimating equations. Since the average reward is a number, we can find the expression for the estimator explicitly, as shown in this slide. Here, Pn is the empirical average over n trajectories in the data set, the standard notations. Here, I use the terminology nuisance functions to call this u pi and omega pi, because the parameter of interest in this work is the average reward. So we treat this u pi and omega pi as some nuisance functions. So a nice property of this plug-in estimator is the so-called doubly robustness. As long as we can consistently estimate one of the nuisance functions, the plug-in estimator is guaranteed to be consistent.
I mean, a quick question. So in general, estimating W is hard, and there's been sort of like the dual dice and other nice work to do that. Will you talk about particular choices for estimating?
Yes, I'll be talking about that. Right. this is coming up in the next few slides. Yes, just yes. So I will be talking about how to estimate these nuisance functions. Just to give you a quick overview of that. So in this work, we will consider using a flexible non-parametric estimator for both of the nuisance functions, u pi and omega pi. As we will see in the next couple of slides, both estimators involves solving a coupled or a nested optimization problem. But due to the time constraint, I will only be talking about like the high-level ideas, and go rather fast. But feel free to look at the archive if you're interested in more details. So let's start with how we estimate the value functions. So the estimation of this value function is based on solving the Bellman equations for policy evaluation. The solution of the Bellman equations is unique up to a constant for the q pi. But for the purpose of estimating u pi, which is the difference of the relative value functions, we only need to learn a specific version of the true value functions. Right. So for a given eta and q, we project the so-called Bellman arrow to a non-parametric function class g, and we will denote the projection by this g hat, and it depends on the policy pi we are evaluating, and also depends on the eta and q. Since the Bellman arrow is 0 at the true average reward and the value functions, we will minimize like the square of the projected Bellman arrow over all possible eta and q in the function class f to obtain the estimator for q pi. Notice here we are directly projecting the Bellman arrow to a space G as opposed to like estimating the Bellman operator, which is more which is often used in the literature. The reason why we project the Bellman arrow instead of the Bellman operator is the left hand side of this is this conditional expectation. The reason why we did that is because we use that to relax the assumption that the Bellman operator has to be closed under the function class G for all possible functions in F, which we will see later as we talk about the theoretical results. Here another thing to notice is that here I used F and G for two function classes. In practice, these two function classes can be chosen to be the same up to a constant shift. But to emphasize like the two different roles of the F and G in the estimation procedure, in particular, F is used to approximate the value function, and G is used to approximate the Bellman arrow. We will use two different notations just to clarify that different roles. So this is the estimation for the value function. Now I'm going to talk about how we can estimate the density ratio in a similar fashion. So we first we introduce a scaled version of the density ratio. We call it the E pi, and this scaling ensures that the expectation of the E pi under the stationary distribution is 1. Similar to the relative value function, we can define this little q pi. Essentially, you can think of it as an MDP, but now the reward is changed to 1 minus this E pi. Because of the scaling, this 1 minus E pi, the average reward for this new MDP is equal to 0, so that this value function is well defined. Right. So it can be shown that this little q pi can be characterized as a minimizer of some objective function similar to the square of the Bellman arrow. Here, this delta pi is a function of the current state, current action, and next states, and also depends on the q that we are evaluating. This is similar to a TD arrow. This is similar to the TD arrow, right? And we can use this characterization to motivate the estimator. Similar to the case of value function, we minimizing we use this g hat n pi of q to denote the estimator for the conditional expectation of delta pi given a q, and we're minimizing the square of this arrow plus some penalty term. Right, as Emma just mentioned, there is growing literature about how about the estimation of the density ratio, those dice estimator. Most of the methods are the so-called the mini-max based methods, which is quite different to the methods presented here, as we are kind of solving a coupled optimization. The reason why it's a couple is because the objective function here involves solving another optimization problem. The advantage of this coupling estimator over the existing minimax methods is that it's easier to control the overfitting by using this regularization term, and it also allows us to directly derive the error bound for the density ratio estimation. When the function space are reproducing kernel Hilbert space, we can find the closed form solutions to the estimator similar to the minimax estimator. But here we have to pay additional computational price. The computational complexity for this coupling methods is higher, as we have to invert the kernel matrix. Well, which we don't have to invert any kernel matrix in the minimax based methods. Right. So now I'm gonna go over briefly talk about some of the key assumptions for our theoretical results. So our first set of assumption is on the policy class. We will use this P to denote the dimensions of the parameters in the policy class. We assume for every policy in the class, the induced Markov chain is irreducible, so that the average reward becomes a constant. We also assume the parameter space is compact and with a finite diameter. The most important assumption is that we assume the Lipschitz conditions on the policy class. This Lipschitz conditions is used to control the size of the class of the relative value function for all the policies in the class, and also to control the size of all of the density ratio in the class. Right. The second set of assumption is for the estimation of the relative value functions. We use this f. We use this norm without any subscript to denote the average square norm across the t decision times. Here the expectation is taken with respect to the distribution collected under the behavioral policies. We use this e pi to denote the Bellman error for a given eta and q. And we use this g pi star to denote the projection of the Bellman error on the space G. So the first assumption is that the true relative value function is correctly specified. And we also need to assume that the zero function is in the space of G. Our second assumption is essentially on the complexity of the function class G. By restricting the eta and q such that the Bellman error has norm 1, we assume that the infimum of the norm of the projected Bellman error is greater than 0. In the case where the function class are all linear function class, this is akin to kind of assume the smallest eigenvalue is positive. We do not need to assume that all of the Bellman error is correctly modeled by G. Instead, we only need to assume that the space of G is just rich enough to ensure that this infimum or this smallest eigenvalue is strictly positive. Yes. And we also make a similar assumptions on for the density ratio estimations. We also have this projection to denote the on G and we also need to assume that this little q pi is correctly specified by the function class f. Here, remember the e pi is the scale version. It's a scale version of the density ratio. So instead of assuming like the zero function is in the class of G, in the case of value function estimation, here we need to assume that this scale ratio is correctly specified by G. And we also make a similar eigenvalue type assumptions on for the complexity of G. Our last assumption is on the function complexity. This is the classical entropy conditions on the two non-parametric function class, and alpha is a constant between 0 and 1. For simplicity, we kind of use a common alpha for both function classes. The larger value of the alpha, the more complex of the function class is. Right. So with this, and so now we can. Now I'm going to talk about the regret bound. Here, the k is an arbitrary integer. Under some additional regularity conditions, if we can choose the tuning parameter appropriately, the regret, that is the difference between the optimal average reward in the policy class and the average reward of the estimated policies, can be bounded up to a constant by the square root p over n, p and plus the p times the n to the power of negative beta k. Here p is the size of the policy class, and the alpha beta k is given here. The alpha is the constant between 0 and 1 in the matrix entropy conditions. We see that beta k is converges to 1 over 1 plus alpha as k goes to infinity. The constant k is not used in the algorithm or used in the estimation. This is only used in the proof. By choosing, as long as k is greater than 3, this beta k is going to be strictly larger than 1/2. So ignoring the dependence of p, the regret bound is essentially 1 over square root n. So the key to the proof is this doubly robustness structure. This is used to control the estimation error of the average reward due to not knowing the two nuisance functions, and the uniform error bounds for the two policy dependent nuisance function estimator. Even though we see a similar structure for the two nuisance function estimator, it turns out that it is technically more involved to bound the error for the density ratio. The reason is quite subtle, but at a high level, it is because we no longer have the zero Bellman error at the true functions. To get around this, we come up with an iterative procedure, and that is exactly the reason why we have this k showing up in the regret bound, and this is only for the purpose of the proof. Another thing to
just interrupt, I think there's a question on there, which is on slide 14, is there an upper bound on the value function? Or in general, do you assume the value functions are bounded?
Yes. This is part of the regularity conditions, right?
Thanks. And also, can you remind me what alpha is again?
Oh, alpha is in the matrix entropy conditions here, measuring the complexity of the two function classes.
Okay.
Right.
We don't get anything in terms of the rates of convergence of how many samples are needed to realize, like what the error is in estimating the nuisance parameters. That doesn't appear in your final.
Yes, this is part of the proof, but I didn't show it here. Yes, we do have a explicit bound for both of the nuisance function estimator.
But those bounds don't appear in the theorem, like the rates, those rates, or do you just assume a certain rate of convergence?
Oh, we actually proved the rate for both of the nuisance function estimator under these assumptions.
Under that assumption. Okay. All right. Thank you.
Right. Yes. Another thing to notice here is that here I'm kind of focusing on the dependence of the n, which is the number of the trajectory in the data. Obviously, the leading constant will also depends on the length, the time point, total time point, capital T. So under additional assumption on the mixing property, we can get the similar bound in terms of the total number of the transition samples instead of just the n here. Right.
I'm sorry, one other quick question, which is Chebo is wondering how large is C as a function of K?
So as k goes to infinity, this constant unfortunately goes to infinity. But the exact order is some exponential, like 2 to the power of k, something like this. Yeah.
For anybody, if that didn't clarify your question, feel free to just put it in the chat or in the Q&A again, and I can always get you to answer live, or just put in if you'd like me to, if you'd like to ask it in person. Thanks.
All right.
So we have about 4 more minutes or so.
Oh, okay. And we can. Oh.
And sorry, one other question by Gabor, which is, what is the intuition behind limiting your function class to be Donsker, aka that alpha is less than 1?
I can see the question.
Oh yeah, the question from or here I will the question from Gabor was, what is the intuition behind limiting your function class to be Donsker, alpha being less than 1? Are you making that assumption here?
Right. Yes. Essentially, this is like a Donsker type assumptions for the function class,
which
right.
is somewhat limiting. So do you think that's generally reasonable for the types of domains you look at, or is it sort of future work to extend it?
This is kind of like pretty standard assumptions for the non-parametric estimate. But I believe that there is some recent work that extends this kind of results in the supervised learning literature, and I think it can be extended to the setting we consider here as well. Yeah.
Well, why not? Why don't we let you finish, and then we can ask additional questions. Thanks everybody for the questions.
Right, and we can also show the estimator of the average reward estimates kind of semi-parametric efficient under the same kind of set of conditions. Here, the asymptotic efficiency is in terms of the number of IID trajectories. So in other words, for any finitely number of policies, the asymptotic covariance, which is the semi-parametric efficiency bound. Right, and we also have some numerical example just to demonstrate the estimation and how, and because this estimator involves quite some tuning parameters. So this numerical example is just to show we have a method to select the tuning parameters based on kind of like the cross validation, and this simulation is just to kind of demonstrate that the validity of that tuning parameter selection. Right. So just a quick summary of this work. We developed the data efficient estimator to estimate the policy that optimize the long-term average reward, and we are able to establish the regret guarantee. So I think I would take the questions here.
Okay, thank you very much for the nice talk. One of the additional questions that just popped up was, could you clarify a little bit the difference between restricting the function class and projection to a function class?
Let me stop sharing so that I can see the words. Which.
So one of the attendees asked, could you clarify the difference between restricting the function class and projection to a function class?
Restricting to a function class basically just means that we restrict all of the functions in the class to have like equal to 0 at a particular state and actions. That's what I mean by restricting a function class. Projection to a function class is we do that L2 projections. Maybe I didn't understand the question.
I don't know who it was, but maybe they can, because it was an anonymous question, but maybe if they have further questions, they can ask. I know that I wanted to, maybe just before we wrap up here, I know I wanted to build on Gabor's question a little bit more. It does seem like there's been some recent work looking at sort of the, from the econometrics community and others looking at sort of allowing more general function classes, in particular to allow sort of deep neural networks to be able to provide similar guarantees. What are the challenges that I think of, we've done some related work just in the sort of optimal stopping setting for off-policy evaluation, is that we do generally have to make some assumptions about sort of convergence, both convergence rates and sort of asymptotic consistency of the function classes. And to me, that's very hard to know for a lot of real domains. It's particularly if we choose a two-layer deep neural network, how do we know whether or not that really has zero bias asymptotically? So I was curious whether or not you think there are particular techniques that are used to tackle that from kind of a statistical perspective, or if you think that's sort of a similar question that's wrestled with in that community.
I'm not quite familiar with this area, to be honest.
Or I guess maybe at a more high level, my question is, these type of sort of nuisance, these type of estimators tend to assume that we have rates on the nuisance parameters and that they are asymptotically consistent. And I think for a lot of the common function approximators, we tend to use right now in machine learning, that will not always be true. A two-layer neural network may or may not be able to capture Q or W. And so I was curious whether that's something that is an equal concern in statistics, or whether and there's standard techniques for handling that, like changing the function class as amount of data so you can always ensure asymptotic consistency, or whether that's not so big of a concern for some other reasons that I'm not aware of.
I remember there is some research about this exactly same issue, where if you have some bias in the nuisance functions, and you cannot guarantee you have the square root n convergence rate, but I'm not very familiar with the results. Yeah, but I can share with you some recent papers on this problem.
Okay, great. Well, we should wrap up now and move on to the next feature. But Chabo wanted, maybe you could see the Q&A now. Chabo also had, maybe you guys can follow up over the chat messages, but had some questions about the guarantees for the CV procedure, and someone else wondered about non-asymptotic results. So thank you so much for the talk, and I'm excited for the next speaker, who Sean will introduce.